Sunny, did you make it to the cookout yesterday?
No.
Oh,
Yeah.
okay.
Poor people miss condoms.
Hmm?
He miss
Oh, yeah, that's you were also not there. Right?
I had work.
Oh, your work.
Mm-hmm.
and then also miss Sanya miss, Rosa miss.
Oh, so the whole class was not there. So they will blame it on me. I didn't advertise it.
It was just unfortunate. Like, I think it being a Thursday afternoon kind of was weird too.
Okay. Because they tell a lot that, oh, go and tell your students in the class. So I always, so I don't have. You guys were there, I noticed. You have much fun.
We enjoy.
Hmm?
We enjoy.
Yes. Thank you. Get rid of the autofocus, right?
Yeah, if you can from your phone.
Same thing.
Beyond
the end.
I don't know if I can.
Still we are missing someone else.
He's coming. He was coming up.
Yeah.
Oh yeah, something. Yeah. From today. We from today.
Yes.
Yeah. But you know.
I have a lot of grading to finish. I will do that, I think. I should stop giving homework so that I don't have to grade. Huh. Any comments from your side? Exam next week,
Next, yeah.
everything that we today, everything we do until then. Including Monday.
If we get the homework back really bit
Yes.
earlier,
I'll cover it today.
okay, that's okay.
Yesterday night, I really wanted to finish.
That's okay if you can, you didn't finish this, take one. And then just give the feedback from that, then we can share the information and then after that will be okay for us.
I didn't understand.
For example, you can write just one
Oh, one problem, yeah, good. One problem, you mean? From
copy, like for we are 8. instead of grading all 8, you can grade 1, and then if there is a mistake or anything wrong, you can just.
Oh, you think everyone is a ditto copy of each other?
No, I didn't say that.
No.
When you grade 1, and then if there is a mistake, and
Oh, then look
then if
into
you
it.
give the feedback, we can see that copy. And then when you grade other, we can take that.
No, I'll do the whole job grading, yeah. No, I hear you. Today. Let me take it on.
We didn't copy that. That
Huh?
one is clear.
No. By the way, it's allowed to copy, like I encourage you guys looking into each other. But at the same time, when I'm grading, I get a little irritated when everyone is making the same mistake. But I allow, in the beginning, I say that it is okay to look into each other's work. The only requirement is that you write your own. Don't photocopy and.
We didn't put a copy sheet.
When I was a grad student, so we used to get a computer program. So the same thing, we used to always copy, it's just common from each other's. And then there was a computer program homework. So we thought, what is the point in again typing it? So we just copied the file, right?
With the name.
And then we submitted, and it was very serious. It took, I mean, they almost, or whoever the person was, who is a friend these days, but he took it very seriously. But that's why I say that no, you're allowed to do this officially, so that you don't feel any mistake. But typically, normal courses you don't do that. Like everyone is sensitive about this, so be careful. But in my course, it's okay. I encourage it. Okay. We have been talking about analytic function and complex numbers, or complex analysis, you would say. And we have also introduced integration on a complex plane. And we got a nice theorem, which is called the Cauchy's theorem, that if it is an analytic function and it is analytic in a region, whole region, then an integral on a line, if it's a closed line, it will be 0. So we want to exploit that today. These are broadly called contour integrals. So let me review in a sense. So still analytic function value. You have a complex number. So y, you visualize it as x, y. That's called a complex plane. We can use polar coordinates or rectangular coordinates to represent a complex number. But this linear combination is important. And a function f of the complex number is an analytic function if f is analytic at p equal to a if that means in what direction you take the derivative, in what direction you approach to calculate the derivative is independent of it. It is equivalent to saying that if you were to write f as two functions, then you have partial derivatives satisfying this condition. These are called the Cauchy-Riemann conditions. So that's the derivative. So once you have a derivative defined, and if it is analytic in a whole region, so this is integration. If And this is a contour integral, so again you have a complex plane. You can pick any contour, C. It has to be a closed path. It's called a contour, and we will have a notation that it has to be always counterclockwise. You can think of clockwise or counterclockwise. When it is zero, it doesn't really matter. But later on, we will talk about residues and all that. So whenever we are doing a contour, it's good to say that it's always having a sense of direction in it. And this is equal to zero. So that's what we showed last time, and I hurried a little in the derivation, but hopefully that was reasonably clear as to why that is the case. So again, analytic function, it has a derivative, it is isotropic, it doesn't matter in what direction you take it. And if it is analytic in the whole region, that means everywhere at every point it is analytic, then it will be equal to the contour integral of that will be equal to zero. So let's take an example. For example. Let's say you have f of z is equal to z squared. It is analytic everywhere except at z equal to infinity itself. And here, and let's say the contour we are interested in is a unit circle. How would you evaluate that integral? Say I want to evaluate this. Remember, this is a when I say this is a contour integral, this is a line integral. So I want to pick what that line is, what parameter decides that line. If it's a circle, what is fixed is r. R is fixed, so it is the angle that is changing. Let me say that's my angle. So I make a substitution, substitute z is equal to, it's a unit circle, so it is r e raised to I theta, where r is equal to actually what? Since it's a unit circle. dz then is equal to r is equal to 1, whatever I have is e raised to I theta, and I differentiate it is e raised to I theta, d theta. So there is r, I have set r is equal to 1, then I differentiate, so it is only theta that is coming in. So that's my differentiation. And the limits on this contour will go from 0 to 2 pi, right? So theta can start from 0 and going the whole circle, it is 0 to 2 pi. And dz is I, e raised to I theta, theta, and z squared is e raised to I theta, the whole square. That's equal. Can come out 0 to 2 pi theta exponential of 3
theta.
I theta. That's a easy integral to do, exponential integral. Or even before I do that integral, I can expand that as cosine and sine. Since I go from 0 to 2 pi, both cosine and sine, they are going from the whole cycle, so it will be 0. Like cosine and sine in the whole period will always evaluate to be 0 because it's positive. So that's indeed 0. So that sort of is a very simple example that demonstrates that. But the main idea I wanted to convey is that this is a path integral. So you always have to pick a parameter. A circle is easy to do, lines are easy to work with. In general, any curve is easy to work with if you know the equation of the curve. So you always want to have a parameter that picks that path or the quantity. So let's exploit this further. Remember a pole. A pole will be, if you can write a function f of z is equal to g of z over c minus a, where g of z is analytic at c around, let me say instead of at around c equal to a, and f of z is analytic if c is not equal to, except at c equal to a, right away it has it goes to infinity. So this is called a pole. So z equal to a is a pole of this function. G of z and nevertheless is analytic. So what can I say about integral of f of z? On a contour, so this is having a here, so that's your a, and that's my contour. So what can I say about z, f of z? Can I say anything? Can I use this?
No, it's not analytic.
Because f of z is not analytic at z equal to a, so in that region, it is not allowing me to use that, but let's exploit that anyway. Let's do the following. Let me expand that a little, make this diagram a little bigger. So let me call that contour C1. And right when it reaches here, so somewhere here, let me break that contour into this. So this is C1. This goes in here, and this is C2. Oh, is that correct? Oh. So I will come in here, and C1 is here, so C1 prime will be opposite to C2. C1. Is that clear what I mean? Maybe. Then I have a closed right here. So that's what I want. So this will be here. That's C1 prime. It's clear. If I were to make this closer and closer, they will be going one way and the other way will be opposite, so they cancel each other. Contour integral or any integral a to b is the same as minus of b to a. So they cancel in this region. So what we have is that integral of f of z in this whole region is equal to 0. Okay, so C1 prime plus C2 is equal to 0. Is clear? Because it is analytic everywhere in this region. I've avoided that point, so I went around it. So when I'm the region I am integrating, it is analytic everywhere. So if that is a that's good. So I can write this as
Okay, for the we are doing the anti-clockwise for clockwise for now. Previously we did for C1 clockwise,
Exactly.
anti-clockwise.
yes.
And then C2 become a C2 dash or just C2 is okay.
I will do that in a minute. So if you allow me, so this is C1 prime, right? EZ, f of z C1 prime plus C f of z is equal to 0. That's clear. So if I take this onto the left hand side, or take this, yeah, this is C1 prime. That should work. And if I go one way, it is exactly equal to minus of the opposite way, so I get my C1 back. So then it is in the right direction. One. It's done.
Is C1 interval, is that no longer closed? Or
C1 is, so this is the, as I squeeze this out, this will be equivalent to C2. And this will be C, so C1 will also be in this. And everywhere in between, it is analytic.
Okay.
And to get that complete closeness, if you want, I can make it open. Or another way of looking at it is that this region is bounded by two regions, like two boundaries, right? This is two boundaries, that's the two boundaries. Right, or C1 plus C2. Different ways of seeing it. And so eventually, what I mean is C1 is Z, f of Z is equal to a small tiny C2, which I will say is exactly on a circle. Correct? 50? Not satisfied. Pradeep?
Okay, over here, we have like a C1 is equal to C1 dash minus C1 dash is equal.
So maybe I did use that C1 is equal to minus C1
C1 dash.
This is equal to C2 Z G of Z over Z minus A. And I can expand this out, maybe I should. Since G of Z is analytic. I have a Taylor expansion for it. And the first derivative. So we have integrals of the kind. So we have first is G of A times plus this is A. Is that clear? Water this integral. What will this integral be? Around z equal to a. Will this be and what will this be? These are all powers of z minus a, correct?
Yeah.
So let's try to evaluate. Let's start with the second one. Let's just C2. And notice the C2 is a really tiny circle. I can make that as small as I want. There is a lot of freedom there. I had a contour C1 to begin with. That's what I'm interested in. C2 is practically there is a infinity at z equal to a, but I can get as close to it as possible. So let me say the radius of this is epsilon. So this C2 has radius epsilon. So I can substitute, it's on a circle, so I'll substitute z epsilon e raised to I theta. And our understanding is that I want to take the limit epsilon tends to 0. So I do the integral, z is epsilon I e raised to I theta. There. And substitute it in here. Integral goes from 0 to 2 pi. dz is epsilon. What is that integral equal to? 0. The integral is 0 because it's an oscillator integral. But even before that, in that limit, this is also 0. There are two zeros coming in, so but there is no conflict. There is a challenge when there one is 0 and one is infinity. Only then there is a challenge. So this is indeed 0. This goes to 0, that goes to 0, this whole thing goes to 0. Now with that idea that this is indeed 0, let's come back and do the first term and see if it is indeed going to 0 or if there is a conflict in that. So let's do dz times e times a. Again, this is contour C2 epsilon tends to 0. Here it really did not matter because I should have been more careful. Yeah, the substitution I made is not perfectly correct. This is z is equal to epsilon e raised to I theta, that's here. Right, that's the origin. That's my epsilon. Right? C equal to epsilon e raised to I theta is on a circle around the origin. But I have an A here somewhere. And C2 is going around that. So I have to add that A, and this is my epsilon. Correct? So I should have had an A there.
The both are going to have different epsilon.
Yes, they should be in general, in principle different. Yeah. But I don't even want that integral. I don't, this was a mistake, right? I should have had an A plus there to begin with. But this is the same. When I take the dz, A is a constant, it goes away. And this whole integral that I did will come out the same, but I should have begun with this because I'm centering around z equal to A. C2 is here, and that's C2. That's C2.
First one is here.
First one is nothing actually, that was a mistake. This was a mistake, so it should have been A plus epsilon I here as well. Is that clear? No confusions? Wait. I want to do the same thing here, C2. But now Z equal to A comes in the denominator. So I substitute Z is equal to A plus epsilon e raised to I theta. So Z minus A is epsilon e raised to I theta. And dz is still epsilon I e raised to I theta. It's the same arguments there. But when I'm substituting, notice what happens. The limits goes from 0 to 2 pi still. Same idea. dz has epsilon I, and in the denominator there is another epsilon. Here there was an epsilon here, the integral is also going to 0. It was almost helping, the two integrals were helping to make it 0. But is this 0? In the limit, the zeros cancel out. Like when you take the limit, so it is not really 0. It's a finite quantity. In fact, exponentials also cancel out. And what you have is exactly 2 pi I. So that's a quantity you will see coming again and again, 2 pi I. That will always go around whenever there is a pole. It will pick up this 2 pi I because you're actually doing the angular integral. And the I is coming from the differentiation in there. So this is exactly equal to 2 pi I. So what you have here is this integral is 2 pi I times g of A. What can you say about other powers? So now that we have a little bit of handle on how things are working, what will this be equal to? This came out to be 0. This came out to be finite, like not 0. What will this be? Zero, and what's the argument? Okay, that's correct.
Well, they don't cancel out anymore.
They don't cancel out anymore. That is all. That is the main idea of Cauchy's theorem, that in this whole series, there is one particular term, only one that cancels, right? This cancels out. It's the same idea as derivative. In derivative also, one term cancels out. But here it is an integration that is happening. One term cancels out and it doesn't go to 0. Rest everything unambiguously, nicely goes to 0. And this is again 0 for all powers actually. So what we have is as if the theorem, if you had to say, if you have any integral of the kind, z, if g is analytic and you have z minus a, bring in a 2 pi I onto the left, that's equal to, if g is analytic, then this will always be just g of a. There was a very similar thing that you saw when we were doing charges, a delta function, right? A delta function used to whatever is there, it will just pick up. So same idea here, this is making it infinity, this is making it 0. They're balancing out each other, and it is evaluated only at z equal to a. Similar feature, but here it is much more powerful, but it's the same idea. So one infinity and one 0 are coming in. So we are going to use this, and this will be called a residue, right? This is called a residue. This is a residue. if I were to have z minus a the whole square, I can redo the whole thing. Instead of z minus a, if I had a z minus a the whole square, which term will contribute me? It will be this that contributes.
Yeah.
Right, this time it was this one. Here it will be the derivative that will come in. Because there is a second power, that is what is going to cancel. If it is third power, or you say pole of third order, it's the next one that contributes, and the same, the argument is exactly the same. The other power starts contributing. Is that clear or not? How about this? Show me as a quiz. How, what happens if this was z minus a the whole square? Repeat this analysis for pole of second order. That's a nomenclature for that, pole of second order. You repeat this analysis for a pole of second order. So now we want to start using this as a in doing integrations and application, let's say.
I have one.
Yes, question. Yeah, any question. This is an important piece here. Yes.
Yeah, for this 2 pi I, can we see picture how that increase into pi I?
Increase.
Yeah, because our like a final answer is 2 pi I that we can see in picture, yeah. I just want to.
How to? I can tell you it's originating from here because they cancel out. Exponential cancels out, and it is an angular integration that is coming in.
That goes into pi I means 2 pi means 180 plus 180 plus 180, that kind of.
Correct. I think that's all that is.
Okay.
Since you asked, let's do one more. Yeah, so maybe there is the impression that goes in here is that it is only in this limit that happens.
Yeah.
So let me consider an integral. Yeah, let's do the following. Let me have a complex integral z over z evaluated on a contour C, and this is on the contour is on a radius r. I see, and this will depend on r, right? Like, that's the only quantity it will depend on, so there is no other parameter. What will that be equal to?
So it has a pole at z equals 0, so you have to take the residue for z equals 0.
And what's the residue of the equal 0?
It's a first order pole, so 2 pi I c g of 0. G is. So,
That would be correct. G of c is 1.
Yeah.
Because there is nothing about that. So let's do this explicitly. You don't have to really use this residue theorem. Like Jackson was really using it, but let's explicitly do this. Like we just have to go back here and make the substitution. And that's what I encourage, that every time do it from the start. Like we don't have to use the residue theorem. So this is any contour integral, that's my contour. On this contour, what is the parameter? Always substitute it, that's theta. So z is equal to r e raised to I theta. Always find a parameter that parameterizes that curve. Here it is angle theta, r is fixed. Right? There is no epsilon now. Epsilon got replaced with r. dz is there. So find dz, that's I r e theta. With me? Substitute it, integrating on this contour and start from 0 and 2 pi. You can start from anywhere.
you just get to
Right.
this pad.
pi by 2 to however you do that. So it is just I can select that to be 0 to 2 pi. dz is I times r e raised to I theta divided by r times e raised to I theta. Notice the cancellation. This was what you were asking as to can you see that 2 pi I where it is coming from? R cancels out. Doesn't really have to be that epsilon. In this case, we exploited the fact that it's going in the limit because we wanted to cancel all the others. But in this example, we don't need that. We don't need that limit going to 0. Here, even for a finite, even R could be infinite. This could be on the edge of the complex plane. Even then, it is 2 pi I. That's big statement there. Even though the contour is going to infinity, it still will be 2 pi I because this cancels out. I have I 0 to 2 pi theta, that's equal to 2 pi I. What happens when R is infinity? It's still 2 pi I. Right? That's not obvious. You would have thought that, oh, this might R is going to infinity, but they cancel out nicely. Right? So, and we will exploit that when sometimes we have to go all the way around. At infinity, we will exploit this fact. Is that clear, Christians?
Yeah, thank you.
Okay, so let's say we are interested in doing an integral. I is equal to say I of A is equal to minus infinity plus infinity x over x squared plus a squared. And x is real. What is that integral equal to?
Arcane X.
Oh, no, but this is definite, right?
Oh, but definite, so. What's I? I don't know if the limit is, as arcane as.
So that's correct, tan inverse. So, but if you evaluate the limits, I think it comes out pi over 2 or 2 over pi.
It's pi over 4 was higher.
So let's quickly do this. Because this is what we want to evaluate. Have space then. Let me substitute, right? Usually you substitute, so x is equal to a tangent theta. Just a substitution, okay? This is standard elementary integral. And you would do dx is equal to a secant square theta. Okay? When x is equal to infinity, theta goes to pi by 2. And when x goes to minus infinity, theta goes to minus 5. Right, that's the information I need to do that integral. So I have I of A. Although one would think that it depends on A. Does it depend on X? It doesn't because it's dummy, right? X is integrated out after you do the definite integral. It doesn't depend on X. So this is equal to when X is equal to minus infinity, so it's minus pi by 2 plus pi by 2. Dx is A secant squared d theta divided by x square is a square tangent square theta or plus a square. What is 1 plus tangent square theta? Secant square theta, so that cancels out. And what I have is 1 over 8 times minus pi by 2 plus pi by 2 times d theta. That's pi, so it is pi over 8. It's not pi over 2, it's pi over 8. Any questions there? I'm going to do the same integral just to demonstrate how we can do this on a complex plane. In this case, it is trivial, it seems unnecessary, but many integrals that are not even possible to do on a real plane. It doesn't mean that the integral doesn't exist. It's just that we don't know how to do it using elementary functions and might be handy. So what in this case, how do you do this? So again, I of a is minus infinity to plus infinity dx over x squared plus a squared. Draw a complex plane. Where does x show up? X is real. X is real here. This is x, that's your y. This is now a complex plane. When I go from minus infinity to plus infinity, where will this be? On the real line. And I'm doing this integral along this line here. Let's say that's minus r, that's plus r, and then r tends to infinity. R tends to infinity. But that's not a closed integral. So we cannot use our power of Cauchy's theorem. So we want to close it. So that's a trick. So I will close it, but then that is no more the same integral. Right? Our integral is on the real line. I want to use Cauchy's theorem. Cauchy's theorem requires a closed integral. So I'm going to change my integral. So I'm going to change my. I would like to do this way. I don't know this, but my guess is I'm going to try this out. And let's try that out. So this is C1. That's C2. Just labeling it. Is that clear? On C1 is my integral. So I'm going to call I of A would be equal. On the complex plane, I have to integrate over C1. I replace x with dz, z now. Because along the horizontal line, along the x-axis, z is equal to x. Okay. Along the x-axis, z is exactly equal to x. So that's the same thing. But this C1, that's not, it doesn't help me because that's not Cauchy. I cannot use Cauchy's theorem.
Use C2.
So now I'm going to do the whole thing. So I'm going to create a new function now. So this is a new integral. Because it's a different path, E of A. This is going to be C1 plus C2. And that's a closed contour now. And I do the same thing. What is the answer to that? Is it 0? No.
That goes to the whole.
It is not 0 because this has poles, right? Remember, this is equal to 0, or it is only if the denominator doesn't go to infinite or go to 0, only then I can use Cauchy's theorem. But nevertheless, I know what it will be. This will be equal to, or let me write this more explicitly. Yeah, let me do it slowly. Let me for now say that it's not 0. Because it's not 0, because it has a pole, z squared plus a squared is equal to, because z squared plus a squared is equal to z plus ia times z minus ia. How many poles does this have? 2. But how many are relevant in this? How many are inside the contour? Where are these poles? One is a plus ia,
The first one.
one is a minus ia. This is plus ia. This is minus ia. So it is this one that contributes. When z is equal to ia, it is inside the contour. When z is equal to minus ia, it is outside the contour. Is that clear?
Yeah, we didn't need a second part.
Yes. Okay. So. This is equal to. C1 plus C2. dz. C plus IA. Minus IA. And what will that be equal to now? This time I can really calculate that. It will be equal to the 2 phi I times the residue. What is the residue? 2 pi I times, strike this out, strike the pole out. After I remove the pole, whatever is remaining, I have to evaluate it at the value of the pole. Right? If I strike this out, whatever is remaining is Z plus IA. So it is 1 plus Z plus IA. I had to evaluate it at Z equal to IA. So that's my pole. Is that clear how I did this? No. Here, hide the pole. Whatever is remaining, I evaluate it at A. Right? And multiply it by 2 pi I. Hide the pole, whatever the function is remaining, I evaluate it at A. So here, if I hide the pole, what is remaining is the other piece. I evaluate it at Z equal to IA, that is the value of the pole. Right? It is not Z equal to A, it is Z equal to IA now. And then 2 pi I multiply it. Is that clear what I'm doing here? Okay, yes.
Why is Z minus IA the pole if it's not in the contour?
This is this is equal to 0 when Z is equal to IA. This is equal to 0 when Z equal to minus IA, right?
Okay.
That's minus IA plus IA. Yeah. Right? If by any chance I had chosen to do this the other way,
Next one we.
then it will be the other one that will contribute, and we can try to do that again because I just randomly picked it to the upper side. You should be able to do it from the bottom and it should give the same answer. It should not care. Unless there are some infinity of other things coming in. With me till now? That's equal to IA, so this is doable, 2 pi I. And that's
2 IA.
2 IA. I cancels out.
2 cancel out.
That's pi over A. Is this the same as this? Is it?
Yeah.
Did we prove that this is equal to pi over A?
Oh no, you have to take out.
We haven't, right? This is not our integral at all. Right? This is not our integral. We added one whole big piece in there. This is, we haven't done anything close to what we wanted. Right? But we happen to have that answer. What that means is that this integral, upper integral, better come out 0. Right? That was half the integral. When you were doing the Z integral, and we did the full integral, apparently we got some 2 pi I. Apparently half integral is supposed to go to 0, but this is a different integral altogether. So let's try that. Is that clear what's going on? Okay. And remember there is an R tends to infinity also. This is not a normal contour, it's on the surface of the complex plane. Okay? So go back to G of A. This is so what we have shown is that G of A is equal to pi by 2. G of A has two pieces. One is I of A plus contour on C2 of dz over Z square plus A square is equal to pi over A. Is that clear what I'm doing? G of A has two contours. One,
I think
C2.
over here we have I of A is already pi by A. And over here we have.
No, this is pretend that we don't know this. We are trying to prove this. Right?
Okay.
So we would like to evaluate this using complex integral. This was just preparing. Oh, we know this, let's check this using complex integral. Most of the time, we don't know the answer. With me? So I'm interested in evaluating this. That is on the horizontal line, the x-axis. But even though I'm interested in evaluating that, I'm not going to do that integral. Most probably that's hard to do. So the hope is that this is an easy integral to do. If that's an easy integral to do, plus the residue gives you the answer. So the whole trick of complex plane is that along one line it is hard, come back on another line because it's zero, whatever is the other one, plus a pole will give you the answer. It's like saying using if gravity is conservative, if I go to one galaxy and then come back, what's the work done by gravitational force? Zero. So if I know one part of the curve, the other part has to be negative because it is zero. So same idea here, you know that either it is zero or it is a residue. So this might be a hard problem to do. So the trick is to find a contour where one is hard and the other is easy. So you've solved an unknown or an unsolved problem because of Cauchy's theorem. Is that clear, the strategy that we are using? You find a contour where one region is doable, the other region is not doable. Together we know the answer, so we know part of it. So that's the strategy. So I'm going to use that strategy, but here to complete that strategy, I have to be able to do this. This should be an easy problem. You're pretending that this is a hard problem. So this should be an easy problem, so I should be able to do this integral. So let's do C2 now, right? So let me write this down again. I of A is equal phi of A minus C2 is Z squared plus A squared. On the contour Z2, it's on C2, right? I know it can use more space. So on C2, Z is equal to R times E raised by theta. Same as the earlier argument there. dz is equal to IR e raised to I theta d theta. And that is all we, oh, that's not, again, I'm making this mistake. I don't want to go with this as the center. I want to go around IA, right? I want to make this as my center. So let's make this I times A, right? Go around the pole all the time. So plus R e raised to I t. But my derivatives will not change because that's a constant. Z, that gives me the advantage that C minus IA is equal R times e raised to I theta. Z is equal to IR e raised to I theta. In this case, actually, you wouldn't have changed even if that was the other way, because in that limit it will go away. So let me do that integral. So C2 dz over Z plus IA C minus IA. That's equal. Angle goes from 0 to pi this time, because it's only half. It's 0 to pi. So it's 0 to pi.
1 part goes cancel.
EZ is I times R e raised to I theta. Theta. Denominator has two R's. Z minus IA is R times e raised to I theta. And Z plus IA is IA plus plus IA plus R e raised to I theta. Is that clear? Provided I just made the substitution, but the main idea is that R, one of the R cancels out, there is still an r remaining in the denominator. We are taking the limit r tends to infinity. So in the extreme limit, its denominator, the whole thing will go away. So let me specify that a little better. You can do this as I and 0 I theta 2ia plus r e raised to I theta. And I take the limit for r tends to infinity. When r is very large, whatever a is, eventually this will dominate. When that dominates, it's in the denominator. This is harmless, it is 0 to 2 pi, there are no zeros coming or infinities coming in. Whenever there is an infinity, the only thing we have to worry about is that is it getting balanced somehow. There are no zeros happening here, there is no zeros coming in. So this infinity will dominate eventually in the denominator. So this will go to 0. Or which you could argue right away here. There is an r here, there is a 2 r's here. So eventually one of the r goes away, so that's 0. So this is indeed 0, so that's pi over. Let's do a very quick problem since we did this very similar, but this time we don't know the answer. Here we knew the answer. Correct? So let's say, and it will change significantly, and this will not be 0 there. Any questions here? Yes.
Is it necessary to make R go to infinity each time you're doing these? Or?
Oh, okay, again. Our goal was to convert or find a path along which you can come back and be able to evaluate. If I don't take the limit infinity, then I have to evaluate this integral.
Yeah.
This integral may not be easy to do. If you can, good. But another reason why you need infinity is that this is minus infinity.
Oh, okay.
Right? So you had to go minus infinity, right? When you go there, come back.
I was just making sure that if the bounds are infinity in the original integral, that
That led to
that's not independent. So it's dependent on the integral bounds.
Correct.
Okay, that's what I was.
Somehow you want to close the integral so that you can use Cauchy's theorem. In your homework, this will be on a unit circle. Like it doesn't have to be always half the main trick in using contour integral is to find the contour. It's like doing Newton's laws problem. Most of the time, the biggest challenge is to identify the forces. All the problems we do in 205 to 200 level courses, or for that matter, the whole of physics, we have done those problems. We are redoing the problem that someone else has done. So someone has already identified the forces, and then we do the algebra. But if you're doing it for the first time, the hardest problem is to figure out which force is acting. Often we don't know which force is acting. Identifying the forces itself can be hard. Same thing here. Identifying the contour can be hard, but what we are doing here is that we are doing contour integrals which others have done. So you work on some 10 contour integral problem, suddenly you're seeing that, oh, I know contour integral. But if it's a new problem, it will be hard to figure out which contour to pick. That's the challenge. But it's not very hard either. The key is to remember, hard problem, find an easy problem. Make a contour
for our benefit,
Correct.
like make it
Yeah.
easy.
You don't be lazy, right? There is an integral that you want which is hard. Want to be lazy, you pick the easy integral. You just have to close the integral. That's a cleverness. So okay. 10 minutes. So let's say this time, very similar integral. And presumably it's doable. Yeah, that's doable. I was thinking of taking exactly the same thing. But let me change it, x plus I or x minus. Okay. Is x is real, by the way? You don't even have to say when you say dx minus infinity to plus infinity, the understanding is that it is actually on your life. So this integral is being done on here to here, right? R to minus minus R to plus R, and R tends to infinity. I have only 10 minutes. This is a quiz for you. I'm going to close it the upper side because I know that is the right one. But you have to figure out why the bottom one is not okay. In this case, both work. In this case, the bottom one is hard. Remember, you'd always find an easy one, right? So in your quiz, you attempt that and you see what goes wrong. And the main idea is that it won't go to zero. It's when you figure out. So is that quiz clear? Quiz is you will have to close it from the bottom. Unless I made a mistake and I will, the upper one is the wrong. One of them usually is wrong. Is the quiz clear? But try to do it from the bottom. Let's say this is C2. This is my integral, but I don't touch that integral. Instead, I say I do another integral which is on a complex plane. C1 plus C2 and R going to infinity. And dz e raised to iz over c minus ie. Clear? What is that equal to?
Not.
It's not zero, very good. And what is that equal to? It's a residue. Hide the pole. So there is a pole at z equal to ia. That's the pole. It's inside the contour. So a residue exists, hide the pole, evaluate the remaining at ia, right? And there is a 2 pi I. With me? Then hide the pole, whatever is remaining, evaluate it at e raised to ia. This has two pieces to it. First one is I of A itself. Second one is C2 times dz e raised to iz over z minus ia is equal to 2 pi I times exponential and z. So even though I'm not integrating the given integral, I'm evaluating another integral. And the hope is that either this is doable or it is zero. Minus of C2 strategy clear? Do this integral, always go around that pole. So z is equal to ia plus r e raised to I theta. That's my substitution I make. dz or z minus ia then is r e raised to I theta. dz is equal to I times r e raised to theta. Theta. And the crucial part, I'm going to is equal to 2 pi I. Again, 0 to 2 pi, not 0 to pi, right? Not 2 pi. 0 to pi. dz is I r e raised to I theta. Theta. Denominator is r e raised to I theta. So the r's cancel out at this point. Now the exponential part. I times z, which is r. Z is this, right? So this is z is equal to IA or IA plus. IA plus r cosine theta plus I sine theta. I want to make sure that this goes to 0 if there is a chance. If it is not, that's also okay. But this is equal to this IA plus r cosine theta plus IR sine theta. Exponentials goes away, r goes away. It's equal to 2 pi I e raised to minus a minus this exponent. This part of the exponential comes out, e raised to minus a I times e raised to minus a. Take the limit r tends to infinity. Exponential IR sine theta and exponential of I square is minus. What happens to the exponential IR cosine theta as r goes to infinity? How does this function behave as r is very large? Does it go to 0? Does it go to infinity? Or does it, is it neither? Is it harmless? No, there is an exponential of I is cosine and sine. Right? So this is oscillatory. Oscillatory means it is +1 -1. That's the maximum it can go. Right? Even if it goes to 0, I don't care. 0 is harmless. And so this is well-behaved function in the limit r tends to infinity. What about this? This is not oscillatory. This is decay.
Decay.
For large r, this goes to 0, does it? What about the sine function?
It goes back and forth.
What if sine function was negative?
Then, yeah,
The next one goes.
Then it goes to infinity, right? So then you are in trouble, because if it goes to infinity, then I don't know what my answer is. So what is sine positive or negative? Here,
This should be.
That's positive.
because 0 to pi,
This.
sine function is always positive. So it is indeed decaying. This doesn't happen when you go below. Sine function in the bottom contour is negative. So it blows up.
Yeah.
So you cannot go down. It's not that you cannot, you can, but then you cannot evaluate this integral. So it won't help you. So a hard problem leads to another hard problem. So you want to solve a hard problem by converting it into an easy problem. So if you go to the bottom half, yeah, it's perfectly okay, but it didn't help you, that's all. Here it helps you. So I chose that in the right direction. Is that clear? Good. So that's in the limit r tends to infinity, this goes to 0 because of that exponential, and then you know the answer. But without that analysis, it's not complete. Right? Because that's what led you to the right contours. That's very crucial. Even though it is 0, often what happens is that because we are doing homework and textbook, we forget that this is very crucial. Right? But that whole analysis is very important. Does that?
Then.
Your homework will involve these things. Always, you want an integral, construct another integral which is trying to evaluate it in another region. A hard problem is getting converted into an easy problem. That's the whole point. So there are only 3 or 4 examples, but hopefully that is sufficient practice. Let's stop it.
For quiz,
Uh-huh.
if for now we did the positive side, the sign, The negative sign, that one is only infinity.
Yeah, so you won't be able to do.
Yeah.
So you converted a hard problem into a harder problem.
Yeah.
So not a good idea. So you say that, oh, I'm stuck. So you stop. Or you can do, now that you know this answer, right? You can use that and can you now do something else out of it? Sometimes you can do double time, right?
We can try that.
Yeah, you can try that, but probably
The
not.
answer will be not come out.
Yeah, probably not, because it is infinity. Once it's infinity, you cannot capture much out of it.
We have to just change the sign and then go this is infinity. Thank you.
Okay. Hopefully this time it works.